I'm very honored to invite up our next speaker, Nicolas Pinto from Apple, who's focused on mobile deep learning. And he's going to talk about how a neuroscience and artificial intelligence researcher turned entrepreneur and then sells his company to Apple. Nico.
Thank you very much. Nice hat.
Thank you. Nice hat.
Good morning, everyone. So, my name is Nico, and I have 10 minutes to talk to you about the past 10 years, where I went from being a neuroscientist at MIT and Harvard, then moved to create a stealth deep learning startup in the Silicon Valley, and finally sell it to Apple. Oops. Let's go back in 2006, about 10 years ago. So that's when I started to work with neuroscientists Jim DiCarlo at MIT and David Cox at Harvard. And they had a very interesting approach. They both wanted to do reverse and forward engineering of the brain in the same lab. Usually these things would be done in different labs, but they wanted to do both in the same lab. And I thought the approach was very interesting. So they really wanted to study natural systems, so real brains, the system that works, and also build artificial systems at scale that approach natural systems, so really big scale. So what do we see when you study natural systems? Let me go very quickly here. So the first thing we see when we study the visual cortex, we're focusing on vision, obviously, is that it's basically a deep neural network composed of many layers that are kind of share the similar properties. Computational properties are kind of similar, repeated patterns. And a lot of these properties have been described in the literature. Many studies from the 60s have described these things in the physiology literature. So you can look at them. What other things we saw is like, if you look at the modeling literature, there are many different ideas about how this thing could be working. Starting in the 60s, this thing doesn't work really well. Many different studies, many different models, many different ideas and parameters. It's really hard to switch the slides. Many ideas, and ultimately culminating in convolutional neural networks that probably you've heard of. These convolutional neural networks have been popularized by Alan LeCun in the machine learning community, but also by Tommy Poggio in the computational neuroscience community with the HMAX model. And so all these models kind of look the same, kind of look very different. You don't really know. And what's very interesting about them is that they have very specific details, and some of them have to do with learning, some of them have to do with the architecture, and the learning details kind of matter, kind of don't. It's really hard to make sense of all that. So in terms of the learning aspects, you have many ways you can do learning. Many different ideas about how you could do learning starting in the 60s and moving on from computational neuroscience into machine learning. Many different ideas. I'm not going to go into it, but like so many different ideas, it's so hard to explore this particular space. So what we saw back in the day is that the hypothesis space of all these different ideas and combination of all of them was overwhelming to explore. As a graduate student, you're looking at all this, they all kind of make sense, kind of not really sure how to combine them. And the space was largely unexplored. And if you just take one particular idea, for example here, you will see that one particular idea has many different parameters depicted in red here. And these parameters are many, you have a lot of them and you have a lot of models, and it's very overwhelming. Again, here for deep learning, so many parameters. How do you set those parameters? So the usual formula is that you take one grad student in a given lab. You just take one particular model. Usually the model will be derived from the particular lab. And the size will be limited by runtime. At the time everyone was running in MATLAB. You tweak all different parameters by hand, one by hand, and you hopefully can crush a few benchmarks. You hope that you can get this kind of work published, and you claim success. And hopefully at the end of all of this, you get one PhD. But if you tweak all of these different parameters by hand, like one by one, kind of not really knowing what you want to do, it's a little bit like what some people will call graduate student descent, just taking one grad student and kind of exploring the space slowly at a time. And that's very alienating and very boring. So we wanted to do something a little bit differently. So we would take one grad student, that would be me in this case. But what we wanted to do is test many different ideas and take big models that kind of scale and approach the scale of natural systems. Hopefully, we could crush a few benchmarks as well. Maybe we can even get that published and hopefully get one PhD at the end of the day. So the inspiration, I got it from this guy, Linus Pauling, double Nobel Prize winner. And he told me, he told everyone, if you want to have really good ideas, it's fairly simple. You just need to get many, 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 many different ideas and just throw the bad ones away. Very simple. And in biology, we have a tool to do that. It's called high-throughput screening. Very fancy name, and it's a very beautiful technique that kind of imitates natural selection. So let me show you how it works in biology. So what you do is you plate a diversity of organisms, like you're looking for some organism that will have some properties you're looking for. You allow them to grow and interact with the environment. You apply some sort of challenge that kind of elicits the properties you're looking for. You collect the surviving colonies, and ultimately, you study and repeat until you find like an organism that fits the bill. So in biology-inspired computer vision, you'll do the same thing. You'll generate a bunch of random models from these many, many different ideas, some from you, some from the literature. Apply some sort of learning to learn the synaptic weights and interact with the environment. Test with the screening task, a particular vision task in this case, scheme up the best model, study, repeat, and validate on the task, and hopefully get the properties you're looking for, a really good visual system. What's nice about this particular technique is that even though we call it high-throughput screening, it's basically just brute force, right? I mean, it's a very nice name. We like that as scientists, but it's just pure brute force. And in this particular case, we needed to have a lot of compute power to run all of these models in parallel. But we were back in 2006, and this is basically at a time where these GPUs, these very cheap graphics processing units, started to be very, very powerful and actually programmable. So we got lucky because we found that trend very early on, basically 10 years ago. The problem with this is that it took us a while at the beginning because it was quite complicated to program. So we had to build everything from scratch. So the computers, the software stack, programming OpenGL. It was a lot of fun, but quite hard at the beginning since there was no library for it. We even went as far as building a cluster of PlayStation 3 back in 2007 to get this raw brute force power that we needed for this particular experiment. We also got access to hundreds of GPUs because at the time, national supercomputing centers were building a lot of these supercomputers with tons of GPUs, but not many people knew how to use them properly. So we had access to a lot of them because they wanted to get used. With the brute force approach, you can do that. We also taught these things back in 2008 and 2010 at Harvard and MIT, how to use these GPUs to be able to do more computational science cheaply with these graphical units. So let me skip forward. We basically applied this technique, came up with a model that kind of is all-encompassing, has tons of parameters, and can encompass all these different ideas that I just mentioned, apply a brute force technique, and hopefully, at the end of the day, we basically got very good results, and we are very surprised. And the results that we got were so surprising that even got featured in Science in 2010. Not only we were surprised, but even Jan LeCun himself was surprised, and he told us that some of this work was actually influential in such a way that we uncovered some very important nonlinearities using this kitchen sink approach. So most particularly normalization and ReLU. Okay, let me fast forward. So since we had some very interesting kind of results, we wanted to see if we could apply this to the real world. So we compared our technology to a commercial system called Face.com. It got bought by Facebook. We were able to crush their performance. We even got in touch with Google back in 2011, and they told us that we were basically kind of influencing a little bit of their work, the early Google Brain work back in 2011. So we decided to start a company based on this, and the company was called Perceptio. It was very stealth, so you probably won't see much information about it. The goal of Perceptio was basically to come up with some brain-inspired AI that you can trust. The trust was very important to us. We wanted to make sure we preserve the privacy of users. So why a startup? Well, what we saw is that we wanted to optimize progress, but we saw that academia and industry were kind of optimizing for progress, but kind of not. On one side, you'll have academia where it would be a credit economy. So in a credit economy, what you do is you plant flags and you guard territory. It's all about, me first, you don't really know what's going on. You just have to, plant flags. That's how you get a career. In industry, it's a profit economy. You have to make money. And a lot of times, what that means is selling user data. So we need to kind of create a new organization that will not be operating like this. So we had grandiose ideas like many others. It didn't work out at the end, but we had this grandiose idea of starting this intersection of incubator, industrial lab, academic lab, focusing on progress only. It didn't work out, but that's what we wanted to do. The applications area that we were focusing on was a smart social camera. And our moat, our competitive advantage, was going mobile first. Everyone was going in the cloud. We wanted to bet against the cloud and go mobile first. Everyone was surprised at the time. It was 2012. Everyone was running deep learning in hundreds or thousands of CPU cores or big GPUs. And say, why would you even try to do this? It's not even possible. If you look at it carefully, it cannot be done on the compute side. At the time it was an iPhone 4S, not much compute going on. But ultimately we did it, and a lot of the things that we uncovered back in 2012 are now being rediscovered by the community. Some people claim that we cannot do it because you will not see enough data. Well, it turns out if you're the most popular camera in the world, you get to see a lot more data than the cloud. This camera, if you sit right next to the sensor, you can get dozens of frames per second, and only a fraction of that will go in the cloud. People got it now. We could preserve privacy. Ultimately, we were able to predict the timing of the deep learning tsunami, but not its velocity. So we had to scale with this small company, and the only way for us to scale was to go to an acquisition. The problem with the acquisition is that most of the companies will go about this profit economy by selling user data. So it was really hard for us to kind of find the right home for our technology and scale. So we thought very hard, and we kind of found a little small fruit company back in Cupertino that, as you know, think very differently. They think different about this thing, and they really do care about the user privacy and not selling you user data. So that's where I am right now. That's where Perceptio is right now. And that's it. This is like the end of the 10 years of my life. Thank you very much.